and welcome to B&W's Environmental Equipment and Upgrades Product Introduction Session. My name is Shamara, and I'll be today's moderator. Before we begin, we wanted to emphasize B&W's commitment to safety in our global business operations, in our homes with our families, and even with you today by attending this session virtually versus in person to keep us all safe and healthy. If you joined a few minutes early and were in our virtual waiting room, you learned tips for how to move or dock the AV pod and how to utilize the chat pod to ask questions today. To move the black AV pod, simply click and drag on it to move it anywhere within your browser window. To dock it to the right, click the small double squared button in the bottom right corner of it. The chat pod is your typical chat window where you can type comments and ask questions. We'll be monitoring this throughout the session today, and we'll take questions as time allows. Please be sure, though, to type in your technical questions so we can follow up with you in greater detail over the next few days to get you a personalized answer. For this session, all attendee microphones are muted to allow for the best listening experience possible. We'll also take short breaks today. At this time, I'd like to briefly introduce our presenters who have 71 combined years of expertise. Steve Borsani is Senior Director of Global Business Development at B&W, who specializes in matching customers' project objectives and operational needs to B&W's technology portfolio. Joe Mitchell is an advisory engineer in our Process and Control Engineering Group, who specializes in B&W's environmental equipment. John Cordes is a global project developer at B&W for international retrofit projects and has a strong background in AQCS equipment, specializing in B&W's particulate control technologies. Thank you again to all of you for joining us today. Steve, please begin.
Good morning, everyone. Thank you for attending this session, and most of all, thank you for taking the time out of your busy schedules today to listen to this presentation. Hopefully you will find it informative. I would like to welcome our guests. We have guests from 5 different countries today, including Hong Kong, Indonesia, the Philippines, Taiwan, and Thailand. So with that, I will get started with a brief introduction to the Babcock and Wilcock company, because we do have some customers on this call that are not completely familiar with B&W. So with that, I will start with the introduction to the Babcock and Wilcock company. Babcock and Wilcock, based in the USA, is the original Babcock company. It was formed in 1867 and founded by George Babcock and Stephen Wilcox. We have a strong heritage and a promising future where we are a total systems provider for steam generating equipment, be it fossil or renewable fuels, as well as environmental control systems. We have extensive experience in engineering, manufacturing, and research and development. B&W, again, we were formed in 1867. This is our 152nd year of being in business, and we have a long heritage. You can see we have leading technologies with combustion systems, fluid flow systems, heat transfer, renewables, be it waste to energy or biomass, and then emission control systems. Today, obviously, we will focus on the emission controls. As you went through school and perhaps in your daily business, you're probably familiar with B&W's publication of STEAM. We are now on the 42nd edition of STEAM, and hopefully you're all familiar with that book and find it beneficial. So the Babcock and Wilcock company has 3 main operating groups. We have B&W SPIG, which is our wet, dry, and hybrid cooling systems. B&W Voland, which is our Center of Excellence for Renewable Energy Technologies, and then the Babcock and Wilcox Company, where we have the steam generating equipment and the environmental solutions. Under the Babcock and Wilcox Company, we have two brands that you're probably familiar with, that being the ash handling systems under Alan Shermanhoff, and then the Diamond Power equipment for boiler cleaning. B&W is a shoot-to-stack provider, and what we mean by that is we provide equipment from the inlet of the fuel feed, be it fossil fuel or biomass or waste energy, up through the inlet of the stack, including the complete environmental trains. This slide is showing two different configurations of environmental equipment, which we will discuss today in more details as the session goes on. On the steam generation side, B&W has all available technologies. We have ultra supercritical boilers, subcritical radiant boilers. These are typically utility size units. We have heat recovery steam generators, small industrial water tube boilers, multi-fuel industrial boilers for solid fuels or liquid and gas. We have grate fired units, and that could be biomass or waste energy. We have process recovery boilers for the paper industry. And then we have fluid bed boilers, CFBs, and bubbling fluid bed, again, mainly for biomass and coal in the case of CFBs. We also have a major focus today on waste to energy. We have a long heritage of supplying waste to energy equipment. We have technologies to address both mass burn, municipal solid waste fuels, as well as RDF, refuse derived fuels, and converting that into energy. In addition to waste energy, we have also a major focus on biomass-fired plants, and the issue that B&W brings to these types of projects is we have all three available technologies for burning biomass, that being a bubbling fluid bed, circulating fluid bed, and also a grate or stoker-fired unit. Biomass can be a wide range of fuels, but mostly wood waste, sludge, straw, and other agricultural waste type products. Under our SPIG division, we have cooling system technologies. We have natural draft hyperbolic towers. We have mechanical draft systems. We have air-cooled condensers and air fin coolers. So we can handle the cooling water side of the plant as well. B&W has all available commercial technologies for environmental controls, and that includes particulate controls, NOx control, SO2 and other acid gas controls, SO3 and acid mist control, mercury and wastewater elimination. We will talk about all of these technologies in more detail as this session goes on. So I won't spend a lot of time on this particular slide. In addition to all of our products in our portfolio, we also have a major focus on global parts and service, where we maintain our existing equipment through upgrades and retrofits, replacement parts, optimization, engineering services, and construction services. So we supply the equipment as an OEM, and we also service the equipment for the life of the plant. B&W is, Babcock and Wilcox, I should say, is been in business for 1867. The name Babcock is a little bit confusing in the marketplace. And with this slide, I just want to leave you with this brief introduction to the company of who Babcock and Wilcox is, and more importantly, who Babcock and Wilcox is not. The company was established by George Babcock and Stephen Wilcox in 1867. In 1891, you can see here, we established a separate division in the UK. That division was originally listed as Babcock and Wilcox Limited, and that was in 1891. Babcock and Wilcox Limited then sublicensed the technologies through license agreements in many different countries, and you probably know some of these entities, and I won't go through them all, but I'm sure you're familiar with the Deutsche Babcock entity and Babcock Hitachi and Doosan Babcock, to name a few. Those today have no relationship with the Babcock and Wilcox company. There's no sharing of technologies. There's no financial ties between any of the companies. Only the name Babcock is the same, but there is no relation between any of those companies. The license agreement with the UK company was terminated in 1978. So since that time, we have not shared any advancements in technologies for not only B&W Limited Company, which is now Doosan Babcock, but all of the other Babcock companies around the world. Excuse me. There were various license agreements at the time, and if you have questions on Babcock companies, we can certainly address those one by one offline to explain to you who those companies are and the basis of their technologies. So with that brief introduction, I hope you understand who the Babcock and Wilcox company is, and you will have our contact information as part of this session so that you can reach out to us in the future for any clarifications in that regard. So with that, we will start with our presentations on the environmental technologies. Our plan here is to go through the environmental equipment in the direction of gas flow. So we will start with in-furnace technologies for controlling NOx emissions through combustion process. And then we will go into the post-combustion equipment in the flue gas train. So we'll talk about SCRs, dry ESPs, wet FGDs, wet ESPs, and then towards the end of the session, we will address some dry sorbent injection systems, zero liquid discharge, and mercury capture as time permits. So with that, I will start with the in-furnace technology, meaning low NOx combustion systems. B&W has invested a lot of effort in the development of low NOx technologies. There's a lot of things that are commonly used today by most suppliers that B&W actually hold the original patent for. For example, we were granted the original patent for overfire air systems, which is common in lots of different applications today. We continue to invest in our research and development on advanced combustion technologies. We're looking at pure oxygen firing. We're looking at biomass firing, combination of biomass and pulverized coal as ways to provide a more green solution to the power plants. We have 4 generations of low NOx burners. I will go through a couple of those generations today, And then I will also talk about how we apply the overfire air system in our current projects for low NOx combustion. So this slide is showing the 4 generations of low NOx burners. The first generation is what we call the dual register burner. And while this product is still in service at some plants, we do not offer this product commercially today. In the 1980s, I should say the first generation burner was developed in the early 1970s. In the 1980s, we developed a second generation low NOx burner that we referred to as the DRB, which reverts back to the original dual register burner, XCL. And that generation burner provided a 5 to 10% improvement in NOx emissions over the original dual register burner. Then in the 1990s, we developed the third generation burner, which we called the DRB4Z. Again, DRB standing for dual register burner. The 4Z meaning 4 zones. These other burners, the original DRB and the second generation DRB XCL, were 3-zone burners. The 4Z burner has 4 air zones. And I'll talk a little bit about the 4Z burner in the coming slides. And then the fourth generation burner is the B&W Airjet, which is our most advanced low NOx burner. And you can see here starting from the base of the original dual register burner, the Airjet burner will reduce emissions 30 to 35% below the original dual register burner. So to talk about the 4Z burner a little bit, what you see here is this red portion is a sliding damper that controls total airflow to the outer secondary air zones of the burner. And it's controlling the air through this inner spin vane assembly and the outer spin vane assembly. And this controls, so what the burner does is it provides a separate control for total airflow to the burner versus turbulent air, or the turbulence that's put on the secondary air for proper combustion with the directional spin vanes. The 4Z has a transition zone around the coal nozzle, and it has a separate sliding barrel here, which controls the amount of air coming through this transition zone. And what the transition zone does is it provides a little further delay in the rapid mixing of air and fuel to control the generation of thermal NOx. This slide shows how the burner works in an illustration. Excuse me. And you can see the yellow areas here are the turbulent air, and then this green and red zone here is providing a buffer to delay the mixing of the secondary air to the fuel flame. And that delayed mixing provides a cooler temperature flame, which eliminates the amount of thermal NOx generated through the combustion process. We refer to this as a self-staging burner, meaning that this burner can be applied with or without an overfire air system. You will get further NOx reduction with an overfire air system, but the burner can also be installed in a furnace that may not have the height or proper dimensions to use overfire air. And in that case, you can see more favorable NOx performance without the use of overfire air. The latest burner that we offer is the B&W Airjet. And this burner operates on a very different principle than the original traditional low NOx burners that B&W as well as other manufacturers offer in the marketplace. The difference with the B&W Airjet is we are promoting the rapid mixing of fuels. And what you'll see in this blue area is we are, if you can envision, this is the furnace wall here. And then obviously this is the front of the wind box and the coal coming up from the pulverizers into the burner. Inside the wind box, we have a inlet duct for each individual burner, which is this blue nozzle. So we have hot secondary air entering inside the coal flame, as well as hot secondary air on the outside of the coal flame. And then the coal itself is in this second nozzle entering into the furnace. The principle behind this burner is very different than common low NOx burners. Common low NOx burners is delayed mixing, slow mixing, and controlling flame temperatures to control thermal NOx. What the Airjet burner does is it actually promotes more rapid mixing, hotter flame temperatures, but at a substoichiometric condition. So this burner will operate at a staged condition while still being able to maintain combustion efficiency with controlling the carbon loss during combustion. Excuse me. So what this illustration shows how the burner works in a two-dimension view. It's easier to see. So again, this is inside the wind box, and you have hot secondary air entering in to the inner nozzle of the burner. You have pulverized coal in the second annulus, and then you have, again, hot secondary air on the outside of that coal. So you have air, fuel, and then air again. And what that's doing is it's promoting a rapid mixing of fuel and air. It creates a hotter temperature so we can control the carbon loss through the combustion process. But at the same time, once we get that initial burning or volatilization of the fuel, we are then in a fuel-rich zone. So any emissions that are generated through the combustion process are then offset by longer residence time in the fuel-rich zone before entering into the overfire air elevation. This burner, as I mentioned before, the 4Z burner can be used either in a staged or unstaged condition. The Airjet burner has to be used with overfire air, but it comes with a significantly better or lower NOx emissions than traditional low NOx burners. This is a picture of some Airjet burners in our factory. This damper here would be inside the wind box. This cover plate back here would seal against the wind box during installation. This is obviously the furnace end of the burner. And inside the wind box is this damper arrangement, and it allows the air to enter through the center nozzle of the burner. So again, the center nozzle is air, not coal. The second annulus would be the pulverized coal, and then the outer air zones are hot secondary air. So we have hot air on the inside and hot air on the outside of the coal jet penetrating into the furnace. This is a straight-on view. So, again, you can see some, I don't know how well this shows up, but you can see some turning vanes inside this nozzle. So that's directing the secondary air on the inside of the fuel jet. This would be the coal coming from the mill in the outer air zone, and then the two outer secondary air zones further mixing of the coal and air. And this is an installation of an air jet burner in a new plant that we recently built. And you can see this is the wind box side of the burner. So the damper for the air jet itself would be behind this inside the wind box. This is the coal pipe coming up from the pulverizers, and then the coal nozzle here entering into the burner. So for overfire air systems in a staged combustion, we have our own process that we go through to design overfire air systems. We use a B&W proprietary modeling system that we call COMO. And the benefit of COMO is that we use every unit that we start up, every retrofit that we do, we feed the results of that into the COMO model. So we're able to predict very accurately NOx emissions, whether it's on a new installation or on a retrofit. And what you'll see by the COMO model is what we're trying to do over here is on the left-hand side of this slide is we're trying to get a clean blanket of air over top of the combustion system. Sometimes that may mean we change the number of overfire air ports. It may match the number of burner columns that we have, and it may not. And what we rely on is the model to give us a solid blanket of air with full penetration into the furnace so that we have air available to complete the combustion process at the overfire air elevation. Some of the things that we consider when we're looking at overfire air systems is we worry about the spacing between the burners themselves and the overfire air ports, which are these gray arrows here. And then the red arrow is showing the overfire air ports to the furnace exit. And what we're trying to show by these two illustrations would be a retrofit application, and meaning that every project is very different and has to be looked at on an individual basis, because sometimes we have less residence time to complete the combustion process in some furnaces that we may have in other furnaces. The other thing that we look at for overfire air systems is allowing full penetration of air into the center of the furnace so that we, again, get a good blanket of air over top of the combustion system so that we can complete the combustion process and control unburned carbon or combustion efficiency with the application of low NOx burners. The overfire airport itself is similar to the burner, where we have a device. In this case, we have a total flow control damper that surrounds the NOx port itself. And then we have separate control of the spin vanes, which are these yellow vanes and the control handles here. And then this particular design, we have a disc that controls the penetration of air going into the furnace. So in this blue area is the air penetration that will come in to the center of the furnace so that we know we have air coverage over top of the combustion system. The yellow or the spin vanes are there to provide air coverage next to the front walls and side walls, again, so that we have good proper coverage to complete combustion, as well as to control any formation of CO during the combustion process. The dual air zone NOx port ships as an assembly. This is just showing some illustrations here of the NOx ports, how they would arrive at at site. And then this is a installation of a NOx port. This particular one has two sets of pitot grids in with Magnehelic gauges so that you can adjust the amount of air going through the center penetration versus through the secondary air zone of the spin vanes to control turbulent air and coverage along the furnace walls. So with that, that takes us through the combustion process, and now we're going to talk about post-combustion systems. And I will turn it over to Joe, and he will talk about the SCRs.
Okay, thank you, Steve. And like Steve said, we're going to go through the gas flow here as we come from the furnace, and then now we're going to move on into the gas flow. And first up is going to be the SCR. And you know, obviously the slide here says NOx control. That's what we're going to focus on in this particular part of the presentation. But make no mistake, the SCRs also plays a significant role in SO3 generation and mercury control as well. So we'll try to touch on those a little later. But you can see here that B&W has quite a bit of experience in SCRs, various fuels, various industries as well, refineries and smaller applications, industrial, all the way through utilities, utility boilers. You know, we can use any of the reagents and also catalyst types as well. We do not make our own catalysts, so we can use any of the vendor catalysts that are out there. So this slide, we'll just quickly walk through the SCR. And like Steve said, there's a lot of environmental equipment we have, so I may go through them a little quick, but obviously keep asking your questions. We'll get to them when we can, and we will we'll address all of them. We can add a lot more detail to most of these presentations, but since we don't have a lot of time, we'll have to just stay pretty brief. So here you can see the gas flow as it comes into the SCR. We'll pass through some sort of ash collection potentially if we're expecting some large particle ash. You can see here this is a screen. Then we go into the injection grid. So B&W's technology will actually have a grid where you can adjust the valves in this area here and basically vary the amount of ammonia that you are injecting into any of these particular points. Then we travel from the grid on into the mixing area. So we have a gas mixer, and you know, most of these technologies you'll hear a lot, right? Where flow distribution is important, and in of course the case of the SCR as well. Even the boiler, as Steve talked about from the COMO modeling, we're really trying to work on gas distribution and getting, you know, all the. In the case of the SCR, the NOx mixed with the ammonia, the temperature consistent across the face of the catalyst. So as we move through the mixing zone, we'll then turn on into the inlet of the SCR, down through the catalyst layers. You can see, you know, here we're showing some soot blowers and sonic horns, and we also, you know, air cannons are also a possibility. We'll touch on those as we move through. This particular SCR here has 3 layers of catalyst, and then this here shows a future, so 4th layer catalyst for catalyst management and as the catalyst ages over time. As I mentioned, catalyst selection. So since B&W doesn't make their own catalysts, we can use any variety of vendors, whoever is the most competitive on the project, not to mention, you know, different pitch and different styles of catalyst. So the application, you know, if we're expecting a certain amount of ash, we may go with a plate type or corrugated style rather than the honeycomb. So certainly we have experience with all of these different catalyst types, and again, you know, in the North American market especially, we saw many different types of fuels here in the U.S. with bituminous, subbituminouses, the lignites. So a lot of different ash characteristics and a lot of different experience with catalyst types as well. Again, maybe one of the other main systems that isn't necessarily in the gas flow particularly is the ammonia injection system. and actually the ammonia system itself. So depending upon whether we're using aqueous ammonia, we could be using a urea ammonia on demand type system, or anhydrous ammonia. We've used all types of the reagents. But in general, the same concept. You will vaporize the ammonia, or in the case of your urea, you'll actually generate the ammonia. And then the ammonia will go up into the ammonia injection grid section. And like I said before, down here actually showing the manifold valve station. So part of our tuning process is to adjust each of these valves down here to basically provide more or less ammonia depending upon what the NOx distribution is coming into the SCR. So important factors, we talked about gas flow distribution. So gas flow distribution is very important. Obviously, catalyst type is important. Also very important is the temperature. Temperature into the SCR can be handled with any of these various types of solutions to keep your temperature up to the SCR catalyst and in the range for reaction. And then you can see here something that B&W actually offers is a V-temp economizer. So what this is we can actually vary the flow through the economizer to actually control the temperature as the load continues to go down or up, depending on how you're ramping the load. And this curve here actually shows that and illustrates that for us. So you can see as load comes down, without a V-temp, you would tend to drop lower and lower in temperature, which puts you in a range of potentially seeing some ammonia bisulfate formation and slowing the reaction in the SCR. So you can see here with the V-temp, we can actually maintain a very consistent pressure temperature of the gas coming into the SCR, even at the low load cases. Another important part of your catalyst life, the design of the SCR, is going to be keeping it clean. So the SCR we showed earlier, the cross section was a vertical flow SCR, which would be typical of a coal-fired unit. Now, depending upon the type of ash you have or your expectations on the amount of ash, you could use either sonic horns, probably one of the more common, also one of the more cost-effective as well, or soot blowers if you're expecting a little more difficult ash to handle. And we also have air cannons, which are more for localized ash accumulation. And again, we can provide any of these types of ash removal or ash moving systems. The main point is to just continue the ash moving through the SCR and on into the ESP or the other particulate control devices. But as I mentioned, the ash type is very important. Your typical fly ash, you're just going to use sonic horns, soot blowers to push the ash through. You want to just keep the ash moving, get it onto the ESP so it can get captured and handled. However, there is a lot of times where you'll actually get a large particle ash or popcorn ash. And you can see this ash over here to the right. And this ash cannot be pushed through the SCR. So what happens is that ash actually makes it to the SCR if you do not have any way to handle it. And it'll actually plug the individual catalyst cells. And, as the catalyst plugs, the gas flow distribution changes. As the gas flow distribution changes, you're likely either going to see an decrease in either an increase in ammonia slip, decrease in NOx. Typically, if you see decrease in NOx, you'll increase your ammonia. So very important to keep it clean. So when we encounter this type of ash, we can attack it in a couple different ways. We'll either look at an aerodynamic approach. So you can see here, we would actually install a baffle here. And all that really is using CFD modeling to try to generate changes in velocity and momentum to drop that ash into the hopper and capture it prior to entering the inlet of the SCR. Another alternative is an actual physical barrier, obviously, which would come with a little higher pressure drop, but you actually can size the holes to match the pitch and the size, your actual free passage in the catalyst blocks themselves. So you're basically straining the gas to prevent those large particle ash from making it to the SCR and catalyst surface. As we move on to the ammonia systems, you can see here, anhydrous is probably your most cost-effective reagent, not only from buying the material itself, but also probably your system, your actual anhydrous ammonia system would be the lowest installed cost. But there are regulations, and sometimes there's safety issues associated with the handling of the anhydrous ammonia. And so some plants combat that with an aqueous ammonia. So really all you get is it's a much harder to vaporize. So the aqueous ammonia, you'll need more of it, obviously, and you'll have a little bit more difficulty vaporizing it. And urea itself, typically you would use, you could use a ammonia on demand system. You would make the ammonia on site. So you'll get urea delivered, make ammonia, and that ammonia would then be injected into the SCR. So we've talked about flow distribution being a very important aspect in the SCR. And not only is it flow distribution from a velocity standpoint, but also making sure we mix the ammonia NOx. We need to get that intimate contact with the ammonia NOx as it passes across the catalyst. So the way we do that is we mix. You can see here there's the different types of mixing devices, from vortex, which is blending, rotating, and vanes, which push the gas from side to side. B&W has taken both of these approaches to develop our mixer design. You can see it's supposed to optimize space, pressure drop, and mixing. So you get the best distribution for the pressure drop with a minimum pressure drop in flue length. So that's our philosophy, and you can see here is the combination. So you would have the injection points here. These would all be attached to a throttling valve, so you can throttle the ammonia flow to any of these particular sections. So you would test the SCR slip and NOx at the outlet, and you make adjustments. You would test it at the inlet and the outlet of the SCR. You make adjustments to your ammonia injection grid during your tuning phase of your SCR installation. And you can see it gets good mixing there with the ammonia NOx. And then also, we're like I said, we're trying to keep good temperature distribution to the face of the catalyst as well. You can see here, this is a recent SCR, or one of our more recent SCR installations. You can see the inlet loading of the NOx at 375, reduction rate of 86.7. It's a pretty significant turn down on this unit. There were actually 2 SCR chambers per boiler unit, with a large particle ash collection system, anhydrous ammonia. And you can see this, we're starting to see more and more high reduction rates in NOx. So I think we have a break. Or are we going to move on? Okay. So I think break is plotted in this section. And we're going to jump to John Cordes. And he's going to talk about our primary particulate control devices. And then hang tight. There's a lot more to go here. We have the SO2 control systems, mercury, primary particulate control. So a lot to come up. So get your coffee. Good morning to everybody. Thanks for joining us, and we'll talk to you again here soon.
We're going to take a quick break here for about 10 minutes, please. In the meantime, please take a moment and sign up for our B&W newsletter. It's called The Generator. It's filled with lots of helpful information, so we would love to hear from you. So please take a moment, fill that out. Like Joe said, feel free to stretch your legs, grab some coffee, and we will be back with you in 10 minutes. Thank you. Welcome back, everyone. We are going to tee this up right now to our next presenter, John Cordes, and he is going to be speaking about primary particulate control.
Okay, thank you. Welcome back, everyone. So now we'll get into primary particulate control and B&W's technologies. So here on this slide here, we have our three key technologies to particulate control. I'll talk a little bit about the first two here, dry ESP and fabric filter, and then a little bit later we'll go into the wet ESP. I think generally everyone's familiar with the dry ESP technology. It's the workhorse of the utility industry. It's in most plants in the first device in the AQCS train. We also have a fabric filter technology, more prevalent in the US than Asia. Also can be used as a primary filter, lower emissions traditionally than a dry ESP. And then there's some added benefits when you look at sorbent injections along with the fabric filter. So we'll dive a little bit deeper into these technologies. So first is B&W's electrostatic precipitator experience. We have quite a bit of experience, 50,000 megawatts, 11,000 megawatts of those are on major rebuild retrofit projects as emissions restrictions continue to come into play. We also offer extensive mechanical and electrical upgrades, parts projects, applications from power industry all the way through all kinds of industrial applications. And then I'll talk a little bit more about our two types of dry ESP technologies here, top wrapped and tumbling hammer. First, just to kind of calibrate everyone. So the fundamental equation of dry ESP sizing is the Deutsch-Anderson equation, where collection efficiency is a factor of collector plate area and migration velocity, which migration velocity is really based on each dry ESP supplier's experience base. It's an empirical calculation that you obtain from wherever your experience is in your performance data. That's where we bring, B&W brings unique with that 50,000 megawatts of experience. We can size an ESP accurately for any application, any fuel. So as I said, B&W has two types of dry ESP technologies. On the left here, the European style tumbling hammer design with rigid frame and electrodes. This is more traditionally used in the power market. And then also on the right here, B&W has what we call an American style ESP, where it's top wrapped with actually rigid pipe and spike electrodes. So for those that aren't familiar with the top wrap style, here's a picture of the top of the ESP. As you can see, the gas flow here is on the left, travels into the ESP from the left to the right. You can see the mini wrappers on top of this type of ESP, where each collecting plate actually has one of these wrappers, and it allows you to vary the frequency and intensity of each of these wrappers on each different collecting plate and different fields. So it really allows you to optimize the ESP for your given design conditions. And just here's a little picture zoomed in on what electromagnetic wrapper looks like. This anvil here actually moves up and then drops down to wrap the plates. So again, as part of the top wrap style dry ESP, we have rigid pipe and spike electrodes, which are really reliable. They last 20, 30 years, the lifetime of the unit. You can see here on the first field, it's what we call a V-pin configuration. So in the first field of a dry ESP, you want aggressive corona generation to capture that high inlet loading into that first field. So what we do on the first field is actually put this V-pin style electrode in, and then as you get to the latter fields, we go to a more traditional opposed pin design. So here's a B&W tumbling hammer dry ESP project in Indonesia, 2x700 megawatt unit, where we targeted 50 milligrams PM emission, pretty large ESPs, 2 ESP casings per unit, 4 fields. So again, that's the tumbling hammer style design. And then a recent project at a refinery in Israel where we provided this is a top wrap style dry ESP on a FCCU plant. And startup in 2017. So we can offer both styles. It really depends on the application and the goals of the project. So now I'll dive a little bit further into ESP upgrades, which are prevalent in the market today. So there's a lot of reasons why ESPs are underperforming. It could be just maintenance, operation, mechanical condition, just wearing through the life of the dry ESP, or it could be that conditions have changed from when it was initially sized. So now the ESP is too small, or was originally sized too small, or an SCR has been added, which impacts it. Sorbent injection has been added, or fuel switches. So many reasons why that an ESP might be underperforming. So some of the remedies to fix an underperforming ESP. So the easiest and lowest cost is to restore it back to its original design. So tune up the boilers, the burners, inspect and realign, improve any gas flow distribution issues that may have come up over time, or you can look at upgrades to the dry ESP for if conditions have changed and the ESP just can't get there anymore. So two options: you can increase the collecting area, which will improve performance. There's options there: converting tumbling hammer to top wrap design, which I'll go into a little more detail, adding an additional field, adding a slipstream. Those are all ways to increase the collecting plate area within the ESP. Another option is to actually improve the migration velocity, which you can do by upgrading from single-phase power supplies to 3-phase or to high-frequency power supplies. And along with that upgrade, you can also sectionalize the electrical field. So if you have 2 fields in the direction of gas flow, you can extend that to 4 fields, and that'll improve your performance. So as I touched on in the last slide, B&W has a unique solution to an ESP upgrade, which we call a top wrap conversion, and that's converting an existing tumbling hammer style dry ESP to a top wrap style ESP. And what that can get you is you can actually fit more collecting plate area within the same ESP footprint and improve the performance. So it's really a low-cost capital solution to add more plate area within your existing ESP, rather than adding a slipstream or adding an additional ESP or adding an additional field. This is a low-cost alternative. So this particular project is a top wrap conversion, what we call a top wrap conversion for 2x670 megawatt units in the U.S., where on one unit, actually the unit 4, we rebuilt 2 of the first 5 fields, converting them from tumbling hammer to top wrapped. And then on the second unit, which was unit 5, we rebuilt 3 of the 5 fields to converting from tumbling hammer to top wrapped. And the goal of this project was to reduce the opacity, which we successfully achieved, reducing from 12 to 15% to 0.5%. And then also as part of this project, we had additional scope in SCRs and FGDs and burners as well. So here's just a picture during construction where to reduce the outage time on this particular project, we actually built large modules off to the side, essentially built a full mechanical field off to the side and then lifted it into place. So you can see 15-meter tall plates, 26 gas passages, and 11 meters in width, and we lifted those into place to reduce the outage time. Here's a good picture. You can see where this is the unit where we converted the first two fields. So gas flow enters from the left and travels to the right of the dry ESP. You can see the existing fields in 3, 4, and 5 are still tumbling hammer style design. And in the first two fields, we're now converted to top wrapped. And you can see we added additional plate height. And also the reason we can add additional collecting plate areas, we take up this space which was reserved for the tumbling hammers here after the field. And now by moving the wrappers to the top, we were able to add collecting plate and add area within the same footprint of the dry ESP. So it's a really unique solution to improve the performance on your existing ESP without getting into a lot of civil work and additional site constraints. Okay, now I'll dive into B&W's fabric filter technology. So maybe to start, just a quick comparison to dry ESPs for those who aren't familiar with fabric filters. So an ESP is really sized for one condition or multiple conditions, but it's based on a fuel, it's based on a flow, it's based on a temperature. So as those change, the emission changes on a dry ESP, where on a fabric filter, the emission's constant. So what changes as say, for instance, flow or the fuel changes, the delta P or the pressure drop across the fabric filter changes, but the emission remains constant. So in the U.S., that utilities moved towards fabric filters because it offered them greater flexibility in fuel and just changing conditions on the boiler units. So that's really the fundamental difference. The other difference to highlight is that maintenance consideration. So a dry ESP is pretty maintenance free. I mean, minor alignments, but where you look at a fabric filter, you do have to replace the bags every 4 or 5 years, depending on the design conditions and operating conditions. But there's a little more routine maintenance to a fabric filter to get that constant emission. So B&W's fabric filter experience, 27,000 megawatts, 11,000 megawatts that were on new units, 16,000 megawatts were added after the boiler was installed. Many different fuels, coals, waste, municipal solid waste. We have different configurations, which I'll get into, and also ESP to fabric filter conversions. Excuse me. So a little bit of history on fabric filters. So more stringent utility regulations, emissions regulations in the U.S. really drove fabric filter installations. So starting in the early 70s, pulse jet, what we call pulse jet fabric filters, which is what I'll talk about today, were only being used on small and medium-sized units, and what were called reverse air were used on large utility units. However, more recently, in the 1990s to present day, everything really moved to pulse jet fabric filters because they're low capital cost installations versus the reverse air. And then also beyond the U.S., Australia and South Africa began using pulse jet fabric filters due to the difficulty in achieving emissions with an ESP. So here's just a schematic of a fabric filter. So a little side view here. So the dirty gas enters on the left, either into the hopper or into the bottom of what we call the compartment, travels upwards. The particulate is collected on the outside of the bags, and the clean gas then travels through the bags up through what we call the tube sheet, where all the bags and cages rest, and then exits the compartment through the left here on the clean gas outlet. So the particulate's then collected on the outside of the bags and drops into the hopper and then is evacuated through the ash removal system. The one thing to add here, so these little circles here are blowpipes. This is So on a pulse jet fabric filter, air is pulsed from these blowpipes through holes directly over the bags, which send a shock wave through the bag, which then drops all the particulate into the hoppers. So here's a picture of one of B&W's configurations for a pulse jet fabric filter. You can see the inlet and the outlet manifolds here. You can see the compartment cut out here with the bags and the blowpipes up here. Access to the compartments is through on this style is through what we call a hatch. And we have different configurations. We can size the compartment for different quantity of bags. Inlet outlet manifolds can be on the same side, opposite side. So our design standards really allow for customization to any site constraint. So here's a side view just to give a little better picture for how the gas travels through a fabric filter. It'll enter what we call the inlet manifold on the left here. Gas flow then, you can see the inlet manifold is tapered to maintain velocity and equal flow to each of the compartments. So gas will travel then into the inlet manifold, down through the inlet nozzle, into the compartment, so into the page. It will then travel up through the bags, as I said in that other side view, and exit here through this outlet manifold, and then off to the right out of the fabric filter. What you can see on this side view here is actually bypass dampers located in the manifold. So for startup or excursion conditions, it's relatively low cost to install what we call bypass dampers, where under those unique conditions, these would open up and gas would just travel from the inlet manifold to the outlet manifold and not into any of the compartments. So here's a picture of what that bypass poppet looks like. We call those poppet valves. They're double sealed, double bladed, so that during normal operation, no gas leaks through. Here's a picture of blowpipes, how they're centrally aligned over the bags. You can see here on the right, and those provide the cleaning air to drive off the particulate from the bags. Those blowpipes and pulses, so each blowpipe row is controlled by a pulse air valve, which is fed from a pulse air header, and then the pulse air timer is what controls each of those valves and cleaning through the baghouse. So here's a picture of the bag attachment to the tube sheet. So this area has to be sealed, otherwise there will be emission leaks across. It's very important to seal. Otherwise, there'll be emission leaks across the baghouse. So what we do, we have a snap band connection where you can see in the picture here, they folded the band and then it snaps into place with sealing across the tube sheet. Here's a picture inside a compartment with a bag installation. The bags are going in first. The cages go in second. So depending on the height of what we call the plenum here, which is the area located above the tube sheet, cages will come in 2 or 3 pieces depending on this height. And you can see here, so this is the one piece of the cage dropped into the bag. This one here already has that second piece of the cage already attached. And those are then fed into each of the bags. And here's kind of the after shot, looking up from the hopper. It's important when installing bags in a baghouse to make sure that they're not rubbing against each other, because that will create leaks and premature failure in the bags. So this is a recent fabric filter project that we did in the U.S. here. So what we did for this client was standardize a fabric filter design they had various size units, 500 megawatt units, 750 megawatts, and 1,000 megawatt units. So we standardized the baghouse design across all those units, which allowed us, a low-cost solution to just duplicate these baghouses. Here you can see the after. So this is actually a baghouse with the inlet and the outlet on the same side. So that's just one arrangement that B&W can provide. Here's a construction picture of the compartments being installed. Another thing B&W has experience in is actually converting an ESP to a fabric filter, which this was a project in the Midwest where we converted 2 ESP casings to a single fabric filter. Generally, when you're looking at an ESP to fabric filter conversion, there's usually plenty of size in the existing ESP, because when you look at velocities, a dry ESP is only a size for roughly 1 meter per second, where a baghouse is much higher velocity. So typically you can fit a baghouse within the footprint of an ESP. So this is just a picture where on this one we had a unique manifold design where we arranged separate ducts within the baghouse footprint to each compartment. You can see here how those ducts are arranged. Here's a construction picture with those manifolds going into place. This is prior to the compartments would then be placed on either side of the manifolds here. For this project, we retained the existing ESP hoppers and all the support steel, and then build a baghouse from the support grid up. And here's the after picture. So that's in this construction picture, you can see the compartments are now installed, the tube sheet level here, and then finish work here was the penthouse is then placed on top. Okay, now I'll turn it back over to Joe Mitchell to talk through SO2 control technologies. Thank you.
Okay, thank you, John. As he said, we're going to go through our SO2 control technologies now. You can see we have several different styles of SO2 control. Just depends on your fuel, the amount of removal you need. You can see here we have dry control with dry sorbent injection, so no water required at all. We have semi-dry technologies with spray dryers or circulating dry scrubbers. So those will require some water for humidification to enhance the SO2 removal. Wet FGD will completely saturate the gas, and then we also have a seawater scrubbing technology. So we will talk about all of those. A lot of technologies to get through in a short amount of time. So understand I will try to talk slowly and give you as much information as I can, but please ask questions as you get them, as they come to you, and we will certainly get back to you on any of the questions you have. We'll start with our first semi-dry technology, spray dry absorbers. This is a technology that we actually have licensed. You can see, actually, we acquired a company called Joy 30 years ago or so. And as part of that acquisition, we inherited the license for the rotary atomizer technology. You can see here in the 17,000 megawatts bituminous and sub-bituminous fuels, blends of fuels, quite a wide range of experience on the fuel blends. But in general, it's we would say low to medium type sulfur fuels for here in the U.S. This is the diagram of where the SDA fits in. So you can see spray dry absorber SDA. You can see here it fits after the primary particulate control. So in most instances now, if we were to build a brand new unit, we wouldn't necessarily need the primary particulate control device in front of the SDA, but in a lot of the retrofit applications, you'll have an existing ESP. We'll go ahead and put the SDA downstream of that. And you can see here, sometimes depending on the size of the unit, we may need 2 modules. And then typically you'll see a fabric filter downstream of that. The baghouse works in conjunction with the SDA module. You'll get SO2 capture in the modules. You'll also get capture in the fabric filter. So it works all together. The next slide here is showing the process. So essentially you will buy lime crushed, or typically lime that will need slaked, so you'll add water to it to slake the lime. We'll then pump the slurry into the atomizer, to the head tank here. What you see in green is a recycle system. Those aren't required per se. It's going to vary depending upon your removal efficiency, the amount of reagent required, but essentially you would have to look at the capital cost of this recycle system versus the amount of reagent savings. So, but B&W offers this recycle system as well, and again, it's going to depend upon the economics. Here's just a cross section of the SDA vessel. What you probably couldn't see from the pictures earlier, your inlet is typically split into two sections. You can see here, this is the central gas disperser, close-up view here, and it'll bring the gas into the center of the vessel. You can see here with the spinning, the blades create a spin and a rotation. And also into this top section here, you can see the close-up picture is the roof gas disperser. And the same concept, the roof gas disperser brings the gas down right into the area where the rotary atomizer discharges the slurry into the vessel. And essentially this technology is taking a slurry, and then we're using the gas to dry that slurry. And in that process, you're getting that intimate contact between the gas, the SO2, and the acid gases, and the slurry, lime slurry in the majority of the cases. And you'll end up with a dry byproduct, and you'll tend to run the vessel at an approach to saturation. You'll keep yourself from being saturated, maybe 50 degrees, 40, somewhere in that neighborhood in Fahrenheit. So we will. The gas will then move on with that generated solid particulate, the dried slurry, along with the reactant products, and move on to the bag house. So you saw a close-up view of the roof gas disperser and the central gas disperser. This is showing a close-up here of the rotary atomizer. You can see it spins at a very high RPM, generates a lot of centrifugal force to generate a pretty fine droplet size. We actually do also have the atomizer to provide dual fluid atomization, but our experience and our history proves that the rotary atomizer is a pretty efficient atomizing technology. And you can see the different sizes here. That comes in a standard type size, and you can see the slurry actually gets fed right in here, comes out the wheel here at the bottom. The wheel has little nozzles here that are ceramic, and those are parts that wear and will need changed over time. Here's one of our recent projects. You can see from it's a smaller unit, I guess, here in the U.S. at 225 megawatts. Used the subbituminous fuel, PRB fuel here. And that's typical of an SDA. You can see the inlet SO2 at 1,100 milligrams is relatively low in what we've experienced here in North America. And in this particular unit, it required 91% SO2 removal. The semi-dry technology, this particular technology can get us up into that upper 90s range, but in a lot of cases today, we're seeing 99% removal, which would not, this type of technology, be very difficult to achieve. The next technology, again, is also semi-dry. And again, when I say semi-dry, what I mean is we actually do, it generates a dry byproduct, but we do add water. So it requires water. And typically, again, since we're getting close to saturation, but not getting to saturation, the difference in water consumption between this and a wet FGD is, can vary between 10 to 20%. So water, there is quite a bit of water consumption, but not as much as a wet FGD. And here you can see, again, we're just showing the plant arrangement here with your particulate control. In most cases, we would be anticipating a retrofit application, but again, not always the case. Sometimes you may not have your primary particulate control device, and in a lot of cases, that's how we do. We would see it in an industrial application. And so here's your CDS chamber. This is your reaction vessel, and again, similar to the SDA, you get SO2 capture in the vessel itself, and you also get a significant amount of SO2 capture in the fabric filter. One of the unique differences between a fabric filter here, between a CDS and an SDA, is since the CDS doesn't slurry the byproduct and constantly recycles, it's recycled dry. So your fabric filter tends to be higher in the air. You'll need to build it on higher structural steel to be able to flow the ash back down into the CDS vessel. And similar to the process flow diagram we had saw before from the other semi-dry process, the SDA spray dry absorber, you can see here you feed water to the vessel rather than slurrying creating a slurry and injecting it as a slurry into the vessel. We're actually injecting the lime, the reagent, into the recycle section here, and we would inject that in top of these venturis. We'll show, or underneath the venturis, and the water sprays on top of them. We'll see some close-up pictures here of that. But you can see it's a relatively simple process. So how do we recycle? We would use fluidization through air slides. So you can see these air slides here. We require some specific amount of decline, incline, however you want to look at it. So it needs to actually flow from the fabric filter back into the CDS vessel. So it stays completely dry. And these are the venturis I had mentioned. So the number of venturis will vary depending upon the size of the unit. So an industrial application may have a single venturi or two potentially. In industrial type applications, you can see here, you can get into 6 to 8 venturis, much larger applications. And again, you'll get the gas flow coming up through here. Here's the inlet. The solids, as I mentioned before, get injected below the venturi section, and the water would get injected above. Again, what we're really trying to promote is the mixing through this section. I talked about mixing and flow distribution being important. In this vessel here, you'll get a lot of mixing. A lot of your reaction takes place, moves on from the gas outlet and into the fabric filter or particulate capture device. Just a close-up of the lance, just a spillback nozzle we'd typically use, and these would get injected above each venturi within the CDS vessel. And typically we would have spare lances so you can continually do maintenance and not have to take a lance out of service. And a couple of projects here. A recent utility project, you can see again 270 megawatts. And as we saw in the SDA, it was typically sub-bituminous. That was a PRB fuel. You can see here we achieved 98% removal and down to 40 milligrams on a blended fuel. So here we were burning a sub-bituminous and a bituminous with 4,200 milligrams. So we would think of dry technology as such as DSI can get you in a pretty small range for SO2 depending upon your reagent. If you want, maybe a sodium DSI can get you in the 80% range, but at a pretty high stoichiometric ratio. Then you would move to the SDA, which would be able to get you close to 96, 97% of a 1,000 to 2,000 milligram inlet. And then in the CDS here, you can see that gets you higher in sulfur, can get you pretty high removals. But again, from an overall evaluation standpoint, you would look at this compared to wet FGD, which we'll talk about next. that particular technology has a lower cost reagent typically. So it all comes down to economics on how you would, and what this removal requirement is to determine which technology you might want to use if that option is available to you. The second project here is actually an industrial client. So again, I know a lot of you may be industrial or utility customers, but we do have quite a few industrial applications, installations for our environmental equipment. You can see here that we're actually showing one in particular with, this actual, what John talked about was the fabric filter in it. On the utility, we saw compartments on both sides of this inlet manifold, and in this particular case, we just have 4 compartments in line downstream in an industrial application. And you can see here, this again, we had an SCR on this as well as a CDS vessel, and you can see 93.5% removal in this particular instance. And now we'll move into our wet FGD technology. And our experience list here, we have several, you can see almost 50,000 megawatts of technology. This is a worldwide experience. Our fuels that we have wet FGD technology on, coal, we've designed for ore emulsion, oil, petcoke, lignites, any kind of fuels that are out there that you can burn. The wet FGD is a workhorse that can handle high sulfurs and use a variety of reagents as well. Our largest module that we've installed is 21 meters in diameter, and we also have installed them on much larger units. Our large B&W units that are 1,300 megawatts, we've installed multiple absorbers on those units to handle the SO2 removal. So B&W's history of wet FGD is pretty unique because it's a homegrown technology. There's no license. We've actually licensed our technology to several people around the world. But you can see our experience with many chemistries here, from sodium-based mag lime, magnesium-enhanced lime, or straight lime. But the primary reagent around most of the world is limestone because of its ready availability. You can see B&W's timeline. We actually started researching and looking at wet FGD technology back in the 1950s when the U.S. really started bringing a Clean Air Act and started really looking at how to clean up the air, and SO2 and acid rain was a big problem. B&W was one of the first technology providers back then to consider limestone to be our base reagent. A lot of scrubbers in the early days were built around lime, and we started, although we can design lime scrubbers, we started with limestone. And another unique part of our wet FGD technology that we'll get into is our tray, and that's also something that we started with our original R&D work. So we actually started with packing, moved into a tray, and tray is what we offer today. The rest of the timeline is some installation highlights from our technology. But again, wrapping it up, 1,300 megawatts units are the large ones, but requires multiple units, multiple modules, and the largest module we've made is 21 meters in diameter. You've seen this slide a lot. One last time here, coming from the boiler unit, in this, the wet FGD typically will be the last environmental control technology prior to the stack. But in some cases, as we'll see later, there may be some very stringent particulate control that would require a wet ESP to achieve the low emissions on particulate matter. But in general, this would be our expectation of where the wet FGD would fit in. The process diagram here is limestone based, but would be very similar if it was lime as the reagent. You can see that the reagent's prepared, and in the case of a limestone, it's typically ground up in a ball mill system, a wet ball mill. So we grind that limestone. We feed the limestone into the absorber. We can control pH, sometimes removal efficiency, outlet emission, many different configurations of the control loop to the FGD. That'll control the outlet emission or the removal efficiency that you're trying to achieve. And then your byproduct is pumped from the system, typically a density control. So we'll control the density in that absorber. That helps for performance and also helps define the size of this dewatering equipment. We can design an FGD to give you a commercial byproduct that's sellable or throwaway. And we can do systems that do not discharge liquid and those that we can generate that high quality byproduct that may require a water treatment system. So the cross section of our FGD, again, would like to point out it's the tray is what's most unique about B&W's design, but I'll walk through in a few slides here the other qualities I think that are important in our wet FGD. But in general, you're going to get the gas flow coming in here, and this is your inlet section. So, the piece here is actually our inlet awning. So when we designed FGDs years ago, and this is everybody around the world, there was a thought that you needed to actually quench the gas coming into the FGD prior to entering. And then that moved being below the tray to quench. And now today, we actually designed this awning, and we've done quite a bit of R&D work around the shape, size, the design of that awning to really create a waterfall of slurry over that inlet. So the instant it enters the FGD, it's quenched. And then that quenched gas will then move up into the tray. So B&W's tray design, we can use the tray design to keep the gas flow in the center of the vessel. And I'll show you in a couple slides what that looks like. But we'll do variable pressure drop, variable open area in the tray itself to promote that movement of gas throughout the vessel to keep it in the center of the vessel where your high liquid flux is. And then as you pass up through the tray, again, intimate contact here, up into the spray zone. We'll use high pressure nozzles there to give us a good nozzle, drop it, good removal across that spray zone itself. And then after it passes through the cleaner's gas, then it goes to the mist eliminators to remove any droplets. And then, of course, those are washed and the clean gas leaves the FGD. And down here in the reaction tank, what this is showing here is in situ oxidation. So we're oxidizing within the absorber vessel itself, and then the slurry is recirculated. The oxidation is actually a very important part of the process. You want 100% oxidation, or you want very little. So to prevent any kind of scaling or buildup in your absorber vessels. So making sure you have good sufficient oxidation, good mixing in this tank is very important to prevent scaling in your absorber vessels. This is a picture of the tray. Again, this is to show you what the real live tray looks like. You can see that this is actually a tray that was coming out of a 2-year inspection. You can see the tray's clean. There's no, occasionally you'll find debris. That's the type of thing you'll see that collects here, but not, maybe pieces of the pump or pieces of nozzle. Nozzles fall off. But there's no scaling on the trays. And again, the key to that is keeping your chemistry in line. So forcing your oxidation 100% or preventing it typically around 10 or less %, maybe 15. And again, here I was showing what the tray really provides us. Not only that good intimate contact between the gas and the slurry, but also you can see here is pushing that gas flow into the center of the vessel. And this is very important when you get into the 99% removal, the very high removal efficiency, the very low outlet emissions. It's very important to keep this from happening where you get higher gas flows and a lower flux area along the outside perimeter of the vessel. And with B&W's tray, we can actually help promote that gas flow distribution and keep it in the optimum area here where the high liquid flux zone is. And again, achieving those high removals, you really cannot allow any type of gas bypass internal to the absorber itself. And again, that's part of B&W's tray design. We'll design that specifically for each project. And another key component of B&W's FGD design is our patented interspatial header design. And what this is you need a high amount of liquid recirculation in your absorber vessel. The limitation to that liquid recirculation is slurry pump design. There's very large slurry pumps that have some limitations and require quite a bit of power. What B&W does, with our interspatial design, we can put 2 pumps on the same level. So even though the pumps have limitations, we can make our spray levels. There's no limitation on that flow. So we can take 2 large pumps and combine them into a single level. And then not only does it save you tower space, but then power as well. So now your tower is actually smaller. You can see here, this header is actually FRP, but this graphic really shows it. You would have one recirculation pump feeding this entire side, another recirculation pump feeding this side over here. The spray coverage will still be 100% with just one of the single pumps in service. So pretty unique design. And again, it really reduces power, reduces shell height. 2 of the important takeaways from that. And so the real, I think, competitive part of B&W's wet FGD design is the interspatial headers, the tray. Both reduce the amount of tower design required, the amount of actual tower shell height. And the next slide here really shows that. 2 absorbers designed by 2 different companies for the same removal efficiency, same performance. You can see the much smaller, much shorter B&W vessel on this side compared to the competition. And again, that's the impact of B&W's tray and our patented interspatial header design. So we're doing a lot more work in a much smaller vessel. And experience-wise, we a couple of projects that I think are important to share with you and I'll give you the reasons why. This is, here in the U.S., we actually installed the SCR and the wet FGDs in this particular location. The unique part about the FGD vessels in this particular unit, you can see here, we had 3 absorber vessels for the entire plant. So you can see units 1 through 4 were 190 megawatts apiece, and they were all fed into a single absorber. These 2 absorbers you see here, A and B, we're getting the combination of units 5, 6, and 7. So there's other plants that also had that trust in B&W's wet FGD reliability, that they put multiple boiler units through a single absorber tower. And these vessels here were designed for 98% removal. And you can see here the sulfur was almost 5,000 milligrams. And another important project, again, I think what the takeaway is on this particular project is to show that we have designed and achieved that 99% removal efficiency. So high removal, 99 and greater seems to be the trajectory of today's market. And this particular unit was able to achieve very low emissions and greater than 99% removal efficiency. And similar to our discussion on multiple boiler units into a single vessel, this particular vessel here for an industrial application, one takeaway again, it's our wet FGD technology and industrial application. You saw, the process diagram with grinding the limestone, dewatering, a lot of tanks, a lot of pumps, and in this particular instance, in order to take that utility style design and put it into an industrial product, we had to close couple everything and remove a lot of that tanking capacity, storage capacity, and really couple everything close together and take away a lot of the big equipment to make a really nice compact design for an industrial application. And you can see there this particular vessel with the integral stack design, and the tower was actually made of FRP itself. And we also had the SCR here, which was a horizontal integral to an HRSG. And you can see high SO2 removal here, 96.5, not in the 99, but certainly a high removal with a relatively high application feedstock. Much like John discussed with the ESPs, we offer quite a wide array of wet FGD upgrades. We've upgraded many different types of absorber towers, and I'm sure I have a list here coming up. But when you look at how do you improve an FGD, so wet FGD, you've got some things in your pocket you can look at. You can increase the liquid to gas ratio, so that's usually additional pumps. Maybe you can put another absorber on. If you had multiple installations, you can put an extra absorber in service. Nozzle pressure, increasing your nozzle pressure makes smaller droplets, increases your contact. You can grind your limestone better. The simplest would be to increase your pH. But if you can't do it the simple way, there's looking at L over G or pressure drop is probably the primary ways that you're going to increase that removal efficiency. To give it a little baseline here, if you increase the recycle flow, so increasing your pump flow, so changing gearboxes or changing impellers, can give you an increase in pump flow. That 5 to 20% will typically get you 1 to 3% removal efficiency from about a 90% baseline. Whereas adding a tray, which is, we've added a tray to many open spray tower designs to improve the removal efficiency. Again, the benefits of the tray in this case are pretty impactful, going from an open spray tower to a trade tower. The main thing, again, is the gas distribution. We're changing that gas distribution inside the tower, promoting gas flow into that high flux area, and then, getting the removal efficiency, getting that contact on the tray itself. And then what we're showing here is with 3 inches of pressure drop will give you roughly 5 to 6% SO2 removal from that same 90% baseline. So B&W's tray design gives us that opportunity to use liquid flow, delta P, and the tray itself for contact. And here's a good example of an open spray tower before B&W's tray installation of that unit. And, other methods to improve it, again, increase the L over G or install modern headers. And the story behind this, if you can see here on the left, this spray pattern here has a lot of open area that gas could sneak through. We can improve the header design in old towers to give it that full coverage to make sure that gas does not sneak through the absorber vessel. And that's, again, to achieve much higher removals, much lower emissions. So the key points is that we have done it on multiple types of units, open spray towers, dual loop scrubbers. We have modified and added trays and improved even our own designs over time. And here's a couple examples of that. At 1300, one of the 1300 megawatt units, we actually changed the reagent. So the reagent was a more expensive magnesium enhanced lime. We actually changed the internal arrangement of those absorbers and then added a reagent preparation system for limestone and converted that unit from magnesium enhanced lime to limestone. And magnesium enhanced lime requires a lot less L over G, a lot less contact. And we actually improved it by adding 2 trays and 2 spray levels to these absorber towers. Another one here is this particular vessel, again, was open spray tower. We added a tray, and you can see adding the tray increased the removal from 95 to 99. And actually, this is when I was talking, we've actually improved our own units. And in this particular case, this is a unit where it had a single tray and we added a second tray. So you can see adding the second tray, among other changes to the existing spray headers, increased the removal from 85 to 96% removal. Last one, again, is LCRA. And what we wanted to show here again is even on a retrofit application, adding a tray, promoting the gas flow to the center. We changed the spray headers on this particular application to go from 83% to 99 plus measured. The goal was 98, but we were able to achieve 99 plus on that particular unit on a retrofit application. And then real quickly, we'll run through seawater FGD. Again, this is a licensed technology, different than the limestone or wet FGD that we just went through in that it doesn't have a reaction tank below. Typically, you would spray this seawater up into the spray zone from a basin. Tower velocity is the same. Materials can be the same as a limestone FGD. And a lot of velocities are the same as well. You can see here, from a process arrangement standpoint, very simple. Seawater comes in, you'll spray a portion of that into the spray zone. The remainder of the seawater will pass under the FGD where the spent seawater comes with a lower pH into that basin. That gets oxidized. That's to change the chemical oxygen demand and also to drive the pH up again. So that'll then, after oxidation, go on into the discharge. And just a few pictures here of the seawater FGD in service. And you can see here's an oxidation basin picture as well. And experience-wise, again, this is with our licensor, the Nissan refinery. Again, an application of one of our technologies on a industrial application, and again, with high removal efficiencies. So just to summarize our FGD SO2 control technologies, we have a long history. Our first wet FGD was installed in 1973. First dry in 1982, or semi-dry technology. We have a lot of repeat customers here in North America. We have worldwide customers. Some of you may be on the phone today that have our wet FGD systems. And again, we can build new and also upgrade. Okay, and we're going to move on to final particulate here.
Our 2-hour time limit today. What we were hoping is for those of you who can still stick on the call, we have some other content, some other technology we would still like to cover, and that would be wet ESPs, dry sorbent injection, mercury capture, and zero liquid discharge. So if time permits and you're willing to stick with us, we still have some more content to cover. For those of you who need to drop from the call, we certainly understand and thank you for your participation today with us. We are going to take about a 10-minute break right now so folks can stretch their legs, and we'll be back to finish out our technologies. Thank you. you for sticking with us. We still have some content to cover, and we're thankful that you're still here. I am going to turn this over to John Cordes. We also wanted to remind you to please feel free to submit those questions to us. We'll be sure to answer them over the next few days, so we encourage you to use the chat window and submit those questions. Thank you.
Okay, thank you, Shamara. Okay, so I will cover wet ESP technology as the final polishing particulate control. So just in terms of B&W's experience here on wet ESPs, the majority of those are on industrial units, and that's really consistent globally. There's not a lot of wet ESPs on power units, pretty much in the market only in the U.S. and Japan, where in the U.S. B&W is the leading supplier, 3885 megawatts of wet ESP on power. Various fuels, especially along with the industrial processes on the power side, coal, petcoke, and oil. And then configurations, which I'll dive into a little more deeper, is we have both close coupled to the wet FGD and standalone wet ESP designs. And again, a significant, I don't know how many industrial customers on the line here, but several hundred installations in the industrial marketplace. So what are wet ESPs? If you look in the flue gas train, let me make sure my pointer's on. If you look in the flue gas train, as Joe said, typically the FGD may be the last control device in the train, but when you're looking at low PM emissions, low being 3 milligrams, 2 milligrams, 1 milligram PM emissions, you'll find a wet ESP can be added after the wet FGD as the final control AQCS control device in the train. And that's really to polish the final PM and SO3 or H2SO4 acid mist emissions. So what are wet ESPs? The collection principle is very similar to a dry ESP, where electrostatic charges the particulate and it's collected along the plates. The real fundamental difference between a wet ESP and the dry ESP is that a wet ESP is applied in a saturated flue gas environment. So you're operating below water dew point in the flue gas. So then you transfer, rather than mechanical wrapping like in a dry ESP, you have washing in a wet ESP. And then rather than hoppers and ash handling, you have a drainage system on a wet ESP. So things to consider when applying a wet ESP: the fuels, the ash and the sulfur content in the fuel, what other devices you have in the AQCS train, because all these interact differently, like on the SCR, SO2 to SO3 conversion, SO2 to SO3 conversion through the boiler, dry ESP performance, wet FGD carryover, all those things come into play and need to be taken into account when you're looking at a wet ESP. So this is just a summary table of wet ESPs versus dry ESPs. The main points here, I guess, are the gas temperature. As you can see here, the wet ESP is in a saturated gas temperature, saturated environment. So resistivity is not a factor. Since it's a polishing device, you can size a wet ESP for higher velocity, flue gas velocity, than a dry ESP. So they're typically much smaller than a dry ESP. And then because it's operating in below water and acid dew point, a wet ESP is typically constructed of specialty metals, alloy steels, due to the corrosion characteristics of the flue gas and the acid, whereas a dry ESP is just mild carbon steel. So in terms of B&W's wet ESP technologies, we have, as I said, the vertical flow wet ESP, which is integrated with the FGD. That's this style on the left here. You can see, so the wet ESP is actually within the footprint of the FGD. Or you have a horizontal flow wet ESP, which can be a standalone arrangement placed away from the wet FGD based on a site arrangement. So a little bit more about the vertical flow wet ESP with the wet FGD. So with this style wet ESP, you can still have multiple fields similar to the horizontal style. This one requires intermittent washing versus horizontal, where you can have continuous or intermittent washing for cleaning. There's no external cleaning system with this vertical flow as the water just drains from the wet ESP fields down to the tank. And then it can be supported either by the tower, by the FGD tower itself, which can be done more frequently with new installations, new FGD and wet ESP installations, or separately supported by an external structure, which you can see the picture down here would be some arrangement like that. So if you look at, maybe just trace the gas flow here on the right. So with a vertical flow wet ESP, the gas flow will enter the FGD, goes up through the tray, spray levels, mist eliminators. You still have mist eliminators to remove any carryover. And then here, as you transition into the wet ESP portion of the tower, you may have an expansion joint if it's separately supported, like this structure over here, or this may just be part of the FGD shell. Gas will continue. You can also add test grids in this area here. The gas will continue to flow up through the first field in this picture here. So this is the first mechanical field of this wet ESP, up through the second mechanical field, and out through the final mist eliminator, and exit through the outlet hood. So this is just a cutout of the inside the model, the inside of a vertical wet ESP. You can see the plates here. The important part is that these plates all have a gutter here, so you can actually wash the fields on top of each other. The water will not short out the field below. It will actually drain into these gutters, which then is transferred to the shell and drained back into the reaction tank. And here's just a picture of the discharge electrode system of the vertical wet ESP, where the supports are ran through the shell, and then vertical stiffeners then are applied to the external of the shell to carry the load. So horizontal flow wet ESP, similar to arrangement of a dry ESP, multiple fields. Washing can be continuously washed with lower grade alloys. It's a lower initial capital solution, but higher water usage and frequently results in more maintenance than an intermittent wash where you use higher grade alloys. It's more reliable, lower water usage. Typically, these will require an external water recycle system, unless the arrangement allows that these are placed high up in the air, can be gravity drained back to the FGD. And then if you have the external recycle, typically you'll need to add caustic to balance the acid collected in the wet ESP. And these can be applied side by side, so one next to the other, or they can be stacked on top. So just a high-level comparison, just a few key points when comparing the B&W's wet ESP designs. So intermittent wash wet ESPs, as I went through, has some advantages compared to a continuous wash design where you end up with lower water usage. You potentially can eliminate the recycle and caustic system, especially for the vertical, depending on the arrangement for the horizontal. Lower O&M costs and maintenance issues. Yes, it's more initial capital, but as we've seen in our experience in the U.S., customers are happy with the higher grade alloy intermittent wash designs. And then if you're comparing integrated vertical wet ESP to a horizontal standalone unit or vertical standalone unit, depending on your site constraints, it can be an advantage to get the integrated wet ESP. Less ductwork, smaller footprint. It fits within the existing FGD's shell footprint, lower pressure drop because less flue work. Optimized gas flow, as Joe talked about the benefits of the B&W tray when you're placing a wet ESP directly on top of a B&W FGD with the tray, optimized gas flow directly into the wet ESP, and then also the acid and the caustic handling systems are not required. So here's a integrated vertical wet ESP project that B&W had done in Canada. It was 3 boiler units, 2 new FGDs with the vertical wet ESPs, and we targeted particulate there around 82% removal. We achieved 2 to 3 milligrams out, and also high SO3 removal efficiency as it was a ore emulsion unit. Here's B&W's experience on a horizontal wet ESP in China, very low SO3 emission coming out of this. I think we achieved somewhere around 1 ppm SO3 out of this unit, and very low particulate, low emission levels as well. Again, this is a horizontal wet ESP, and this is the stacked arrangement I was talking about, where the one wet ESP is placed directly above the other. So this is a slightly modified slide that we've been showing throughout the presentation here. As you can see, the emission control options that we've went through as you get through the boiler, the SCR, the primary particulate control, dry ESP or fabric filter, SO2 control, you see the absorber here, and then that final polishing PM removal device, the wet ESP located on top. If you're really targeting that low SO3, low PM emissions in the 1 to 3 milligram range. Okay, I think that's it. Yep. So I'll pass it back to Joe Mitchell to go through mercury control. Thank you.
And thank you to everybody who's still with us. Appreciate your patience. A few more technologies to get through here. Actually, mercury is one of the most exciting. And one of the reasons behind that is that it's actually almost every one of these unit operations has some role in mercury capture. So to elaborate on that, we actually have three different technologies we can offer for it. But as I mentioned, they all relate to SCR, wet FGD, and the interactions between the state of the mercury, whether it's oxidized or elemental, as it moves through the system. And we'll see that there's a lot of advantages to actually having as much oxidized mercury as you possibly can to potentially allow for no pack injection or any other sorbent, as there's other types of sorbents available. But what we offer is actually a fuel additive, so you can add this to the fuel to help increase the amount of oxidation. We have an additive you can add to your wet FGD that can increase the removal across your FGD. And then also, like I said, pack injection. And you know, here in North America, there's a lot of formulations of pack. So depending upon that formulation, you can capture more or less elemental mercury. So again, I said every one of the unit operations that we talked about today has some impact on mercury. So the way we measure mercury, since it's a difficult measurement to make, is from fuel. So measure the mercury in the fuel, then you measure stack emissions. That'll give you your overall mercury removal. Because as you can see from the diagram, you'll get mercury removal in your ash. So bottom ash, the fly ash, and then also in the FGD, you know. So if you had a pack system, then you're also going to add some combination of coming out of your fly ash enhanced by the pack injection. So, and again, not showing here is the SCR. The SCR has a very large impact to the mercury removal throughout your system. So I mentioned what is the phase, what is the form of the mercury in the flue gas? That's what's very important to how much you're going to be able to capture. So again, we call it the elemental and ionic or oxidized mercury. You want to typically have as much oxidized mercury as possible. That oxidized mercury is much easier to capture than the elemental mercury. So if you look at what influences the mercury speciation, one of the main influencers is the presence of halogen gas. So if you look at this chart here for the speciation, if you look at a bituminous fuel, a good amount is oxidized. And the reason why is they're usually high in halogens such as chlorides, right? The chloride in the fuel helps drive the oxidation reaction, not only in the boiler itself, but also across the SCR catalyst. So as you move into like subbituminous and lignites, which typically have lower chlorides, at least here in North America, you see that you get a considerable amount more of elemental mercury. So these types of fuels provide the challenge of capturing that elemental mercury, as oxidized mercury is easily captured by a standard pack and also in your wet FGD. Your wet FGD will capture oxidized mercury. So, when you get into these subbituminous and lignites, you are presented a challenge as to how you're going to either oxidize or how you're going to capture that mercury. So as we continue to look along, pack obviously is one of your solutions. So if you need a really high mercury removal, you need to have a very high oxidation percentage, or you need to inject PAC. And PAC is powder activated carbon. So that carbon has the ability to capture mercury. There's two types of PAC that are generally used here in the U.S. Standard is just standard carbon PAC. It's powder activated carbon. Halogenated PAC actually is a powder activated carbon that actually has, it's halogenated to where it will oxidize elemental mercury to make it easier to capture. Regular PAC is pretty good at removing oxidized, virtually all of it, but halogenated PAC will remove elemental, oxidized, everything. So again, this is all going to depend upon the amount of mercury removal that's required in your application. The system's simple. It's literally it's a truck that would fill a silo, some storage vessel, and then you can do a simple system or one here that we're showing with a weigh hopper that'll actually weigh out the amount of PAC, and then it's transported by air blowers and transported into the flue where it's mixed with the flue gas and mercury capture happens. This example here, I think this illustrates the technologies that B&W has pretty well. So I'll try to run through it here briefly. Again, just to set up, we're talking about a 650 megawatt unit that has an SCR. As I mentioned, the SCR is important to this part. It has a fabric filter. Again, that's an advantage, just that the fabric filter creates a cake across the bags, gives it a little bit more of a removal efficiency as the gas passes through the bag. And that's for things like acid gases, and even if you use a PAC in front of that, and then a wet FGD downstream. So what we're going to see here is low halogen fuel, a subbituminous coal, and you get to see the reaction of B&W's technologies. Again, I mentioned our technologies. Merc Plus is an additive to the fuel. Absorption Plus is an additive to the wet FGD. PAC would typically be injected here in front of a fabric filter. So those are the three types of technologies that we offer. This particular example I'm showing you is just showing the benefits of the Merc Plus and the Absorption Plus in the presence of an SCR and wet FGD. You can see here just halogenating. This is the baseline, so no additives at all. If you measured the mercury in the coal, to the mercury in the stack, you would have 30% removal just from the natural particulate capture. Here we're seeing just additive to the fuel. That additive to the fuel, you can see as we just add halogen, you dramatically increase the oxidation of the mercury and therefore increase the amount of removal. The reason being, the wet FGD will remove a significant portion of that mercury that's oxidized. So if you oxidize more of it, you're going to capture more of it in the wet FGD. So you can see here the trend. Pretty big jump just by halogenating, and then we continue to trend up as you increase your concentration of halogen. And that would be the case too if just in fuel concentration. So without an additive, if you had a fuel that was higher in halogen, you're typically going to have higher natural oxidation of the mercury. And then here you're seeing just the wet FGD additive. So first was coal additive, now we're just adding wet FGD additive. So again, our baseline was about 32%. You can see adding the additive to the FGD increased this to about 38. As we increase the additive, we're getting almost the 60% removal. Then you can see the benefits of both additives. So we went from a baseline of about 32% removal all the way to almost 95% removal. And that is with both the halogenation, so adding halogen to the fuel, adding our wet FGD additive to the wet FGD reaction tank, and you end up with some pretty high removals in mercury. So that example is really shows the benefits of halogen and the extra added effect of B&W's additive in our wet FGD. Dry sorbent injection. So earlier I had talked about semi-dry technologies and dry technologies. Dry sorbent injection is a complete dry technology. It's primarily used here in North America and in the U.S. especially for sulfuric acid control. So sulfuric acid or SO3 in the stack will give you a blue plume. So in order to prevent that, a lot of companies now inject this some sort of sorbent and a dry sorbent injection to eliminate that H2SO4 sulfuric acid mist that they see downstream of their wet FGD. But also with our MATS laws, some units choose to also use that for HCl if they do not have a wet FGD in place. And we're also showing here that you can get SO2 removal, but you need for any real appreciable SO2 removal, you're either going to need a very high surface area lime or also typically a sodium reagent. Sodium will give you some higher removals for a dry sorbent injection. So let's say in the 80% removal, you could potentially get more of that, but again, it comes down to gas distribution. It comes down to number of injection lances and the amount of reagent that you would actually have to use. So again, very similar to the pack system, you use a air blower system. You'll bring it to a splitter here so that the pipe will carry it up to a splitter. Same here. And it'll split that sorbent into multiple lances. And you see here the lances. This is how you will design for removal efficiency. So you'll look at things like residence time, your particulate control device downstream, if any, and then your distribution. So distribution, like any other thing we've talked about today, is very important. So number of lances are important, and the location of those lances is very important. So our last technology here is zero liquid discharge. I have a couple slides here. So zero liquid discharge, what we're talking about is actually taking the water effluent, which would typically go to a wastewater system, and some of the drawbacks of a wastewater treatment system is it cannot treat chlorides. you cannot eliminate chlorides in a wastewater treatment system. That's one of the main pollutants, I guess you'll say, or one of the main components of a wastewater that you cannot eliminate in a wastewater treatment system. The wastewater treatment system will treat many things such as the heavy metals, but it cannot get chlorides. Boron is also another one that wastewater treatment systems struggle to remove. And basically what we do, instead of feeding that to a wastewater treatment system, we'll actually feed the wastewater to a dryer or a salt dryer. So that salt dryer is actually the exact type of vessel, very similar to our spray dry absorber that I talked about earlier. So what that gives us, you can actually run that effluent back to the salt dryer. We can either capture that in a new fabric filter or ESP, or let that go back to your existing. And the advantage we have here is this is a technology we've used for years. We have many installations of spray dry absorbers, and now we're using that to actually dry the salts that come from a wet FGD. So we can dry wastewater effluent or absorber slurry, and there's advantages to each of those. So we have a lot of experience with the SDAs. It translates very easily over to evaporating the wastewater. And I think that's it. Yep. So again, appreciate everybody's time, and glad to see a lot of you stick around to the very end. And then we went over a little bit, but we appreciate you joining us today. Okay, thank you very much.
Well, this does mark the end of our session today, and we hope that you found our information very helpful. We appreciate those of you who hung on a little bit longer while we could go through our technologies. Over the next couple of days, you will receive an email from us that contains today's presentation, a link to a questionnaire because we would like your feedback about today's session, and most importantly, you will have our experts' contact information for Steve, John, and Joe, and we encourage you to reach out to them if you have additional questions. Also, for those of you who submitted questions throughout today's presentation, we will be sure to get back to you with tailored responses. So thank you again for submitting, and thank you for joining again today.